We're now going to look at applications of multi-objective least squares to the general area of control. So a general way to say what control is, it's something where you're going to choose an action or an input to achieve some desired output or result. So let's see how that looks. We'll have an n vector x. That's going to correspond to our actions or inputs. By the way, a very traditional symbol for that is u, not x, but we'll leave it as x here. An m vector y is going to correspond to the results or the outputs of using the input x. So that's what y is. So y is going to be the result. And then the inputs and outputs are generally related by a linear or affine input-output model. And that looks like this. This says that, for example, since we think of x as another name for x is the actuator. That's an old school name for it. If x is 0, roughly speaking, if we do nothing, then the output would be b, because you'd have a times 0 plus b. Otherwise, this affine model kind of gives you what happens if you choose the input to be x. Now, the matrix A and B, they're known, and they can come from all sorts of things. They could come from first principles physics models, or they could come from data fitting, right? That you could actually just fit a data to make this approximately to make this equation approximately hold. Now, the goal in control is to choose x. That determines y. Of course, y is a function of x, and we want to optimize multiple objectives that pertain to x and y. And so that's why we're going to use multi-objective least squares. Okay, so typical primary objective would be something like this. I have a desired output or target output. And my first objective often is, let's see, how close can I get to my target? It measures my deviation from the desired output. Okay, and y desired here is given, this vector. Now, a typical secondary objective is something like this. It's often just J2 equals norm x squared. And the rough idea is that expresses our idea that the input we put in should be small, right? And this leads to some kind of efficiency. You want to get close to the target, but you don't want to do it with a gigantic x. That's kind of the idea. Or another way to do it is you'd have some nominal input, x nom, and your secondary objective might be not that x is small, but that x is close to this x nominal squared. By the way, this comes up in sequential control, where you do this every period or time step or something like that. And a lot of times your secondary objective, x nom, is the previous control action. And so what J2 says is, please do what I want to happen, but at the same time, please make my control action or input this time close to what it was last time. And that encourages smoothness of your control actions over time. Okay, so this is the idea in multi-objective control. Let's look at this is actually a specific example of that, although people doing this would certainly not call it control. But nevertheless, here it is. It's product demand shaping. So here's what's going to happen is you have a set of n products and with a price vector p, current price vector, which is positive. And we are going to change the prices by this relative price change vector delta price, right? So for example, if I told you that delta price sub 3 equals minus 0.1, that means, roughly speaking, we are going to reduce the price of product 3 by 10%. That's what that means, right? Plus means you increase the price. Now, that induces, if you change the price of a bunch of products, it's going to change the demand for them. And these are related by this linear equation. Here, ED is E superscript D is the price elasticity of demand matrix. And it's a matrix where the entries tell you how much the change in demand you get for a product as a function of how much you change all the prices, right, for your products. Okay, so that's your linear model. Now, here's what we want to do. Somebody comes to us and says, that's the target demand I want, delta target. And maybe that matches what our production capabilities are capable of producing. So that would have all our factories and our supply chain running at full tilt. Anyway, that's the target demand. So we would like the new demand that's going to be, or the change in demand, I should say. The change in demand should be near a target change in demand. And that's what J1 tells us. So that's the primary objective. Now, at the same time, we want to get close to hitting our target change in demand, but at the same time, we don't want to change our prices like crazy, and that's a secondary objective. That would be J2. And so that says, please trade off getting close to the target change in demand while not, if possible, changing your prices too much. So that would be a very common thing. And then here we would minimize J1 plus lambda J2. Lambda is this parameter, or some people call it a hyperparameter. And we would adjust lambda and see what happens. And it's kind of clear what would happen, right? If lambda is very small, it says basically, for all purposes, minimize J1. It says get as close as you can to delta, the target change in demand. Okay, delta target. By the way, if ED here is invertible, so it's an n by n matrix. If it's invertible, then basically as lambda goes to 0, you would take the solution, which is just simply ED inverse times delta target. Okay, and that would actually make this thing your J1 0. Okay, so that's how that would do. Now that might, if this inverse, this thing here, even if ED is invertible, this could involve like very large price change, like plus minus 400%, things like that. By the way, at that point, it's not just a question of you don't want to raise your prices by 4x or divide them by a factor of 7. It's not just that you want to do it. It's also that this model is wrong there. That model is supposed to be good for price changes that are plus minus 15%, let's say. And it's not even supposed to model what happens if you double prices or triple them or divide them by 5. So this secondary objective is there to keep the price change from being big. Okay. Now, on the other hand, as lambda gets super big, we're just minimizing J2. J2 says minimize the change in prices. And so what happens is as lambda gets bigger and bigger, this will suggest price changes that are more and more timid. They are smaller and smaller. If lambda gets really big, then delta price, as in the limit of lambda going to infinity, we get delta price equals 0, and that says don't touch the prices. So this is kind of the idea. Okay, and so the idea is the whole setting. You're going to trade off the deviation from the target demand, that's J1, with the price change magnitude, that is going to be J2. Okay, so this is just another example. I would call it control. I think other people would not. And people who do this kind of thing would definitely not call this control, but it's okay. Now I'll mention actually a fairly advanced topic. It's robust control, but we can do it. Robust, of course, means something that can handle changes and, so you would say something like, oh, is your system robust to something? And something is some change, right? That kind of thing. So robust control refers to a control scheme that can handle uncertainty in the model. So this is an advanced topic, but it's well within scope of what we're doing now. So I'm going to tell you about it. Okay, so here what it is a very common way. It's actually quite effective. What it is that we're going to have k different input-output models, and these are denoted with the superscript here. So superscript 1, and these are sometimes called scenarios, or sometimes regimes, like in finance you would hear people say that, like, which regime are we operating in, or which scenario are we operating in. So here we have these input-output models. It looks like that, and what it is you're going to choose a single x, and then we interpret y superscript k as that's the output if the system model k is correct. That's what that means. That's what y superscript k is. Now notice it's interesting here, right? I should say, in applications, these AKs are, if they're wildly different from each other, then it's game over and you should just go home, because if someone says to me, "What?" If you say, "What's your model?" and they say, "Here's my model," and they give you 10 models and they're all completely different, you're just like, "Okay, I quit. There's no point, even going any farther." So normally, in fact, what the AKs look like is they're close to each other, but they're not the same. They're not quite the same, right? So, for example, if we actually obtained these models by fitting on data, then these could be 10 different times. This could be 10 different times that you fit the model. You fit the model on Monday's data, Tuesdays, Wednesdays, and so on. And each time you got a model, and they're not quite the same. They might differ in the second digit, something like that. And that's the situation you should think about here. Okay. So what we're going to do is we are simply we would like y to be y desired. So we'll take this objective, which is the deviation of y to y desired. But this is under the kth scenario, and what we're going to do is we're simply going to take the mean square deviation, something like this, right? So that's how we would do this. Now, I mean, and it's interesting because what it's saying is, someone said, "What are you doing?" You say, "Well, I'm choosing an input x," and they go, "What's your goal?" And you go, "Well, I want the output to look like y desired." And they go, "Cool. How do you do it?" And the answer is, well, it's a bit. What you say is, "I don't really quite know the relationship between x and y." In fact, it could be any of these 10 things. So that's it. And so what you're going to do is you're just going to take the mean. You're going to make the mean square error small. So that's robust control. And this will yield a choice of x that kind of works well under all scenarios. I mean, basically in a mean square sense, it's going to work well in all the scenarios. It's not going to, just pick one and make that one, make one of these 0 and the other's big. That's the idea. So that's robust control. It's an advanced topic, but it's easy to understand. It's also super duper useful in practice.